All right, hello everyone, and welcome to week number 12 of Qubit by Qubit. Hope you all had a good week and enjoyed the lecture on Sunday. We're going to be going into more on quantum mechanics today, so very much picking up from where we left off last week, where we talked about the double slit experiment, and picking up with some of the weirdness of that experiment, another very famous quantum mechanics experiment called the Stern-Gerlach experiment, and going over a few sort of practice problems similar to the ones that you will see on the homework. All right, so quick program for today. We're going to start off with the Canvas attendance quiz as usual. We're then just going to jump straight into the pre-lab Zoom feedback. So we actually don't have any pre-made questions from last week, although if anybody does have questions about last week's content, definitely feel free to bring those up. I'll try to remember to pause at the beginning. Anyway, then we'll get into the main bulk of the lab, which is the pre-lab Zoom feedback, lab content, and post-lab Zoom feedback. Okay, so let's start off with the Canvas attendance quiz. So again, just as a reminder, open up your browser, log into Canvas, and you should be able to find the attendance quiz with lab number 1. That's what we are right now. Should be pretty easy to remember. Today's password is 3250, which, as another reminder, you can always find in the bottom right of every slide in the presentation. So even if you come in late, no worries, you can still fill out the attendance quiz. Now, today's question is another one about sort of thinking back to the first semester. As you can probably tell, we're trying to gather a bunch of feedback right now. How would you describe your experience learning the math that was introduced? And then it'll ask you sort of on a scale of 1 to 5, how'd you feel about the pace of the math content? Now, we are distinguishing here, the math content separate from, for example, programming. So what we were doing on Replit with teaching you Python and that kind of thing. This is more like the linear algebra that we introduced, the probability stuff that we went over. I forget. Oh yeah, and then like all of the trig and complex numbers toward the beginning. How did you feel about the pace of it? Was it too fast, too slow, just right? Let us know in the Canvas quiz, just so that we have that information. I will turn on the chat here. If anybody has questions or concerns about the Canvas attendance quiz, feel free to drop them in the chat. And final point, as always, this quiz is not graded. Again, there's no obvious right answer here, but do fill it out just for the lab attendance. Okay, so let's get into the pre-lab Zoom feedback. So you know the drill by now. This will be a scale of 1 to 5 on how you felt with this week's material. So this is primarily sort of thinking back to the lecture that you had on Sunday. How comfortable do you feel with the material that was introduced? Did it make perfect sense? Did it make no sense at all? Go ahead and let me know. And then also, if there's any specific topics that you would want us to spend a bit more time on today, feel free to drop those in the chat. So here's a quick agenda of what we'll be going over in the next hour or so. But if there's any, if you want me to spend more time on any piece of this, just throw it in the chat. It can be a direct message too. If you don't want other people to see, you can privately message me. But yeah, if there's anything you want me to spend more time on, feel free to let me know and I will do my best to do so. The code is in the bottom right of the slide. So it's 3250. Okay, cool. So I think if everyone's ready to go, then we will get into the lab content. Somebody asks, after submitting homework, it's showing the correct answer. Why? I'm not really familiar with the homework interface, unfortunately. If you do think you are running into an error or having some kind of issue or doubts with the homework, I would say email student@qubitbyqubit.org. That would be the best place for that. Okay, so let's get into things then. Now, as I said before, this is the general agenda for today. The first part is a little bit unrelated. We'll be going over sort of some unanswered and answered questions in quantum mechanics Not directly tied to the rest of the content, but I think hopefully still useful for you all as you learn a little bit more about the quantum computing industry. Then the two main halves of this lab is going to be more on the double slit experiment. So if you stuck around for the bonus content last week, you know what happens when you pass only one electron through the double slit at a time. We're going to revisit that experiment and sort of explore a little bit more about what it means. And then in the second half of the lab, we will go over the Stern-Gerlach experiment, which, like I said, is another really important experiment to sort of understand quantum mechanics. Yeah, we'll do a reintroduction to it, and then we'll go over some examples. And finally, the optional content this week is quite short. It's just a little piece on two-level systems, what that means and how we make them in real life, and why they're important. So that one will probably only be like 5 to 10 minutes right at the end of the lab. Okay, yeah, so we will get to the Stern-Gerlach experiment toward the end. So people who are saying practice with Qiskit, is that referring to something that you would want me to go over? Let's code, okay. Well, I don't have anything ready or set up to code with Qiskit today, although, well, I actually think for the next couple of weeks, we're going to be doing more sort of theoretical physics stuff. I think we have 4 weeks of this. So we had the first week yesterday, second week is today and this week. I think there's 2 more after this, and then we start getting into Qiskit. I could be wrong on that, but certainly just hold tight for the Qiskit stuff. I promise all of the material we're teaching you right now is very relevant and important to understand what is actually going on there. Awesome. All right. So the first part, as I said, a little bit unrelated, but I'm just going to take a few minutes to discuss kind of the way that we tend to think about the quantum computing industry and the different roles that are available. And the way I'm going to start this is by listing off some questions that we don't know the answer to. And I'm going to call these the why questions, because a lot of these are, well, as you'll see in a sec, they are phrased as why does something happen the way it does? So one example, why do electrons seem to, or maybe they really do, interfere with themselves in the double slit experiment? Now, if you were here for the bonus content last week, you already know what this is talking about. If you don't know what this is talking about, that's fine. We're going to get to it in a moment. But this is one of those questions that we don't have an answer to. We observe that electrons seem to interfere with themselves in the double slit experiment, but we don't really understand why this should be the case at a fundamental level. Another question that kind of follows the same idea, why can't we know for sure the results of some type of experiments? So oftentimes you'll hear this called determinism. So determinism just means that we can predict with certainty what the outcome will be, assuming we know exactly what all of the prior setup was. In quantum mechanics, that's not the case. Even if we know with certainty what the setup was, we only know some probabilities of what the outcomes will be. And then final question here, why do electrons have spin? So today with the Stern-Gerlach experiment, we're going to talk more about electron spin. It's not immediately obvious, and it's also extremely hard to do experiments to figure out why electrons have this property called spin. And of course, as you can imagine, there are hundreds and hundreds of other questions that we do not know the answer to. And all of these are completely valid, legitimate questions to ask, and they are the center of research for a lot of researchers in the field. For now, though, we don't really have specific answers to them. We only have competing hypotheses for why they might have certain answers. Okay, so let's look at some of the things that we do know, right? So obviously 100 years ago, there would have been, oh, actually, let me just check chat. Okay, so there was a couple of questions, audio. Okay, yeah, it seems a few people can hear me, so that's probably good. Okay, and then there are a couple more questions about Stern-Gerlach. So I will try and get to Stern-Gerlach soon. Yeah, thank you, Hannah, for the suggestion. Just maybe try rejoining if it's not working for you. And then, yes, I do see Harsh's question here, the difference between 1, 0, and plus minus. We will get to that in Stern-Gerlach. Okay, so some of the questions that we do know the answer to. First one, what are the possible results we can get in an experiment with electrons, atoms, ions, etc.? As I said before, we don't know with certainty what the answer is going to be, but we do know what the set of possible outcomes is. Moreover, we know how to figure out or compute the probability of getting each of those results, right? So in some of the experiments or some of the problems that we've worked through, there was a 50% chance of getting a 0, 50% chance of getting a 1. So we know the possible results are 0 and 1. We know the probability is 50-50. We just don't know how to predict with certainty. And indeed, we think it's not possible to predict with certainty what the outcome will be. We also know generally how we can manipulate the probability to get a result that we want. Now, this last point is particularly important because pretty much all of quantum computing basically comes down to this question, right? Quantum computing algorithms are all about manipulating probabilities so that we get some useful answer out at the end with a high probability. And then just like before, there are tons more questions like this as well. And we're getting new answers all the time. So for example, one famous one that's not, I guess, completely related to quantum computing, but just a couple of years ago, the Higgs field was discovered, and that gave us an answer to the question of why do things have mass? Where does mass come from? What is mass? Now, some of those we still don't know perhaps the full answer, but the discovery of the Higgs field was certainly a step in the right direction. And so now we know a lot more about it. So basically, the field of why questions is slowly shrinking. The field of what we do know is slowly growing. Now, I want to ask all of you a question. Do the unanswered questions, the why questions, why do electrons interfere with each other? Why do electrons have spin? Why is quantum mechanics probabilistic in nature? Do these questions make you uncomfortable? And perhaps a better question is, to what extent do they make you uncomfortable? So you might answer, yes, these things make me super uncomfortable and I need to know the answer. This is basically what theoretical physicists do, right? And some experimental physicists. I shouldn't just say theoretical. These people work on the foundations of quantum theory, trying to answer these why questions, right? And if this is the type of person you are certainly in good company. All three of the people here, and of course, many, many more, would generally fall into this category of people who are trying to answer the why question. Now, there's another category of people who sort of say, well, maybe I'm uncomfortable with those. It doesn't make a lot of sense that we can't explain what we're seeing in experiments. But the most interesting part to me is that I want to work on applications. So here, your focus is going to be more on becoming a physicist, yes, but possibly an engineer and develop uses of quantum theory. So for example, working on quantum computing. So here are just another few people. Again, you'd be in great company if you identify with this answer. And they sort of work on this middle ground of there's some theoretical questions, but there's also some application questions that they find really interesting. And then, of course, on the other end of the spectrum is people who say, do the unanswered questions make you uncomfortable? No, not really. We're just going to take them as a fact and see what we can do with them, right? And these are the people who work sort of the farthest on the quantum computing side, quantum computer science, as it's called here. People like Peter Shor and Love Grover would probably fall into this category. And of course, some of your TAs as well. So I think the point with these slides is just, depending on how deeply you identify with these sort of fundamental why questions of quantum mechanics and quantum computing, there's a different place for you to be depending on how you feel on these questions. Now, one other sort of point that I'll make here is these are not obviously just three categories. It's kind of a spectrum, right? So on one side of the spectrum, you are going to have people who really focus on the why questions of quantum computing. On the other side, you're going to have the algorithms people. And you could be anywhere on this spectrum. So right now, I'm going to throw a Zoom poll up on the screen, and I'm just going to get everyone here to think about this for a minute. How uncomfortable do you feel with these unanswered questions? And go ahead, vote in this poll, and let me know where you see yourself fitting, perhaps. And I'll go ahead and share the answers to this afterwards as well, because I think it might be interesting. Okay, in the meantime, other questions? So this is a good question. If every time the results are not the same, how can one make software and work with it, short of knowing how to use the power, or sorry, yeah, how does basically one use the power of quantum computing, even when they don't know exactly the answers, if they'll be the same every time? So for that, I would say, going back to this slide back here, this final point, I think, is really important to understand. When we start looking at quantum algorithms, you will find that the quantum algorithms don't always give the correct answer, or at least most of them. They give the correct answer with high probability, right? And so what we're essentially doing is maybe you start off with a 50-50 distribution, right? You have a 50% chance of being in 0, 50% chance of being 1. And you want to solve some problem where the answer is going to be either 0 or 1. You do some procedure on the quantum system iteratively, right? So you would keep applying this procedure, and you might increase the probability of one of them to 60, and one of them goes down to 40. And then if you do the procedure again, it will get closer to the correct answer. So it might go up to like 70-30. And if you do this enough times, there's a very high chance that you're going to get the correct answer, which in this case is 1, when you measure the system. So that's how we can sort of utilize these probabilities, even though the very next time we measure, there's still a small chance that we would get a 0. Great question. Okay, cool. So a lot of people have voted. Actually, pretty. Well, I'll share the results. Pretty even results, I suppose, between some of them. Not very many people who are just wanting to run Shor's algorithm, but that is totally okay. Seems like the majority, though, want to work on quantum applications, which is awesome. Quantum engineering is very much an up-and-coming field where I'm sure there will be lots of interesting things to do in the near future. Okay, I am going to move on then. As I said, this first part was kind of detached, not super related, but now we're going to jump into a little bit more on the double slit experiment and specifically measurement in quantum computing. So measurement, we're going to define as sort of the final step of any computation. Now, in classical computing, it looks like this. You have some kind of big circuit, right? So over here, you're going to have AND gates and OR gates and things, NOT gates, whatever. You have some big complicated circuit over here. I don't know what I'm drawing. Hold on. Something like this. You have some big circuit, and at the end of the day, you have a wire that outputs a 1, as an example. Now, technically speaking, you have to measure this somehow, right? The 1 will be voltage on a wire, so you have to plug in a voltmeter, figure out what the voltage is, and then you write down some human readable result. So in this case, it would be a 1. Now, this, if there was an output of 0, you would measure a result of 0. This is fairly straightforward though, right? In classical computing, the output and the result are always the same. It's so simple that we basically don't ever discuss the concept of measurement in classical computing. In quantum computing, as you might know by now, measurement is really important. And the reason is that when we have some output state, it could be in a superposition. And when you measure a superposition, the result is unknown, right? The result here could be a 0, could be a 1, depending on what these alpha and beta numbers are. There's some probability of it being a 0 or a 1. And so in contrast to classical computing, where measurement, you can safely just summarize this whole diagram at the top by saying, oh, the circuit outputs 1. In quantum computing, you can't do that. You have to think explicitly about the procedure of measuring your outcome and how that affects the result. So this is where we come back to the double slit experiment, and specifically the variant that we talked about in the optional content last week. Now, all of the stuff we were talking about last week in the regular lab, like the required content, was firing a beam of electrons through the double slit. And what I explained in the optional content is that there is still a possibility when doing that the electrons are bouncing off each other, hitting into each other, interfering with each other in some way to create an interference pattern. And so what scientists decided to do is to try sending electrons through the double slit one by one. right? So for maybe they send an electron, they wait a second to make sure it had time to travel through the double slit. They send a second electron, wait a little bit, third electron, wait a little bit. So in this way, there's no chance that the electrons are interfering with each other because there's only one going through the double slit at a time. So this little GIF in the bottom right shows what they see, right? So this is obviously sped up by quite a bit because this experiment would have taken a lot longer. But each little dot is appearing one at a time. And each of these dots is an electron that was sent through the double slit on its own. Now, you should be able to see from this that the emerging pattern is the same interference pattern with these sort of bright, dark, bright, dark, bright, dark alternating spots that we saw when we sent a beam of electrons through. Now, this is pretty surprising, right? Because we're only sending the electrons through one at a time. We would expect them to go, either through the left or through the right slit. And so a natural question to ask is, well, can we measure that? Can we check using some experimental apparatus which path the electron took? The answer, it turns out, is yes, we can check that. So let's see what happens. First of all, consider how we would do this on the macro scale, right? So suppose we have a gumball gun, right? So this is, if you don't know what a gumball is, it's just like a large piece of candy. And suppose that we have some kind of gun that's going to shoot out these large pieces of candy at a double slit. Now it's going to send them out in kind of a bit of a random pattern. So some of the gumballs are going to bounce off the double slit. Some of them are going to bounce off the middle piece, but some of them are going to travel through one of the two double slits and go on to hit the screen. Now, if we watch the left and the right, we can predict where each gumball will appear on the screen. Right? If we see the gumball go through the left slit, I mean, it should be pretty clear just from thinking about how this experiment would work that that gumball would hit the screen at position number 1. If we saw the gumball go through the right, it would hit the screen at position number 2. Seems pretty straightforward. Now, what happens if you do this with electrons? Again, we are going to somehow set up an experiment where we can watch the electrons go through the left or the right. So we're basically doing the same thing that we did with the gumballs. We will set up, some kind of measurement device that's going to check, okay, this one went through the left, this one went through the right, and then we'll see if we can somehow predict where these electrons land on the screen. So in order to do this, like I said, we're going to add some little electron sensors. I won't explain more exactly how this is done, but we're going to add these little electron sensors on our double slit. And these sensors' only job is to beep or flash or something when an electron zips by them. So we can just watch these two sensors as we fire our electrons one at a time. And we fire one electron, maybe the left one will go off. And then we fire another one and the right one will go off. And by watching these, we will know if the electron went through the left or the right slit. Okay, so we set up this experiment, we run it, we watch what happens. We know, we can write down on a piece of paper the sequence of left, right, where our electrons went, right? So the first electron we send out goes through the left, second electron goes through the right, third electron goes through the right, and so on and so on. And now we can tell for sure which slit each electron goes through. Now, the question is, do we still see an interference pattern? Well, this is what you would see. So again, here we are just watching individual electrons come and hit the screen. So it's sped up, but every little dot appearing is an electron we've fired through one at a time. And here we have a measurement device to tell us whether the electron went through the left or the right slit. And so at first glance, this seems very logical, right? If the electron went through the left, it's probably one of those. If the electron went through the right, it's probably one of those. Pretty straightforward. Now, the confusing part here, of course, is that we see different results without and with the electron sensors, right? Remember, when we did not have these sensors, we saw an interference pattern emerge even when we were firing individual electrons. But as soon as we add these sensors, now we don't see an interference pattern anymore. So that's really weird, right? If we go back to sort of the gumball example, actually, I'll come back to that slide in a minute. If we go back to the gumball example, it shouldn't really matter. And indeed, you can try this at home if you're so inclined. But it doesn't matter if you have a sensor or not. We always just get these two bars. So there's something strange about electrons, right? It seems that somehow the act of adding sensors to our experiment changes the state of the electron, right? Because clearly the electrons over here are not behaving the same as the electrons over here. So what we conclude from this experiment, which is extremely surprising, and we can try and talk about why this might be if we have time at the end, but the conclusion from this experiment is that measurement changes the state of an electron. Just watching something or measuring it is going to physically alter what that thing looks like and how it behaves. So key takeaway, at the end of the day, the double slit experiment is a very mind-bending and weird experiment. It's been the subject of a lot of research and discussion to try and explain why it behaves the way it does. The key takeaway, though, that really the big thing that you should focus on and the big thing you should learn from this experiment is the following. In everyday life, measuring things does not change them, right? Measuring things doesn't, alter the color or the mass or the charge of something in everyday life. And because measurement doesn't affect things, we usually don't talk about measurement, right? We just take for granted that you can measure exactly the length of a piece of wood or something like that, right? In the quantum world, though, measurement can and often does affect the state of the thing being measured. So in this case, with qubits, when we're working with quantum computers, measuring the qubits themselves is going to change those very qubits. This is the key takeaway of the double slit experiment, that measurement changes quantum states. Okay, let's pause for questions. I saw a whole bunch of discussion in the chat, which is awesome. I'm going to see if I can try and catch up with that. Okay, good. A lot of people are saying it's super weird. That means you maybe not understand, but I would say very few people fully understand this thing. Finding it weird is good. That means that you're properly confused by it. Okay, cool. Yeah, so one person says, looks like there was no interference at all, just like the electron passed from the other slit and landed in a different place. Exactly, right? And so the way to think about it is when there are these measurement devices in place, it is just as if the electrons are gumballs passing through the double slit. What if the gumball hit the edge of the slit? Oh yeah, that's a good question. So there are sort of like edge cases, I suppose. So go back to a slide where I can draw this. Right, so here, if we're looking at our gumball gun, you certainly could have a gumball that literally hits, like bounces off the inside of the slit or something. I think we just generally ignore those cases, like they're unlikely to happen. And so maybe there'll be a few stray gumballs or electrons, but what we ultimately care about is the majority picture of what happens, right? When you have thousands and thousands of electrons, what is the general picture that shows up? And even here, you can see in the interference pattern, this image over here is not an actual experiment, by the way. This is something that we just put together because we actually couldn't find an experiment that had been done like this exactly. But there would be some electrons that hit in the middle for no apparent reason, right? It wouldn't just be like they're totally in these two bars. There would be some outliers, but the vast majority would fit the patterns that we're showing. Okay. Still unclear on how this double slit experiment helps with the probabilistic nature of measurement in quantum mechanics. Yeah, so this is a fair point. I think I'll try to explain the way that I see it. The key takeaway, I guess, is that measurement changes the state of an electron, right? I think that the double slit experiment doesn't exactly explain why, going back to the why questions, it doesn't really get at why quantum mechanics should be probabilistic in the first place. The point of the double slit experiment is to explain why, or not why, but again, to demonstrate, I guess, that measurement changes the state of a quantum system. Okay, so one person asks, what would happen if I shoot a thing with a size between a marble and an electron? Great question as well. I don't have a good answer for you, unfortunately, but I will say that size is not necessarily the determining factor that explains whether we will see an interference pattern or not. It tends to be related to a number of other factors in the experiment and how it's set up. So I think even if you used something much larger than an electron, if you kept all of the environmental conditions around it, perfectly tuned, basically so that there's no measurement, right? So that there's no way that you could know whether this macroscopic object was going through the left or the right. If you really controlled the environment well, then you might see an interference pattern, depending on the type of object that you're using. So this experiment, it was the basis of formulating quantum mechanics as it has been formed. Yeah, this is one of the sort of foundational experiments of quantum mechanics that gave us the rules we have today. I forget if I said this in another lecture or not, but quantum mechanics is what we call a phenomenological theory, which just means that instead of the theory being developed by some genius like Einstein, and then being proven by experimentalists over the following decades. With quantum, we started off with experimental results that we could not explain. And then theorists came afterward to try and figure out why that was the case. So it kind of like happened in the opposite direction, right? Instead of going from a theory to experiments, it started with experiments and then became theory. And this is one of those experiments that was, the first wake-up call that, oh, classical physics is wrong sometimes, and we need new theory to explain what's going on. Okay, so to all the questions about like why exactly does the sensor make a difference, that is a philosophical question. I think there's a lot of competing theories and different hypotheses on why that might be the case. The way that I tend to think about it is that all measurement involves some kind of physical interaction. So for example, when we look at something in real, like, in our day-to-day life, there's no physical action that occurs when we just cast our eyes on something, but there is a physical interaction when photons hit objects. So in this experiment, if these electron detectors were using photons to somehow detect the electrons, well, maybe the fact that a photon hits an electron is enough to change the electron somehow, right? And if we're using a magnetic field sensor to detect the electrons, well, how exactly does a magnetic field sensor work? Usually it will produce some small magnetic field of its own and use that to measure an external magnetic field. So again, you could say maybe that small magnetic field affects the electron in some way. So I guess my sort of interpretation of that is that measurement usually has a physical process associated with it. And you could argue that that physical process changes the system in some way. That being said, I don't pretend to understand this stuff fully either. Like it's just as weird to me as I'm hoping it is for many of you as well. These experiments are counterintuitive and very strange. The reason they're so famous is because they precisely contradict what we would expect in classical physics, hence the need for quantum physics. Okay, so I am going to continue on here to the second half of the lab, which is all about the Stern-Gerlach experiment. Now, I will actually, maybe I'll just make one more comment. A lot of these questions about the fundamentals of quantum mechanics, right? Why we see these weird results, how much of it is explained by quantum physics, all that kind of stuff, they're very good questions. I could sit here and talk about them for hours, right? So I'm just going to try and cut myself off because there's so much to explore here. So if you do have a question that I didn't get to, and I know that there were many of them, please go ahead and post on Piazza. Then we can we can actually take some time to sit down and write an interesting answer for you. Okay, so the Stern-Gerlach experiment. We're going to start off with a brief review of electron spin. Now, spin is one of those things that is often misunderstood. The best way I think to describe it is that it's a fundamental property of an electron. And all we mean by a fundamental property is it's a number or a quantity associated with an electron that doesn't depend on any other characteristics of the electron. So examples of other fundamental properties include mass and charge, right? So if I look at the mass of this pen, for example, this pen always has mass, regardless of whether it's moving or it's accelerating due to gravity or it's spinning or it's in an electric field. It doesn't matter what's happening to this pen, it always has mass, regardless of what's going on. Same deal with an electron. Regardless of what's going on, it always has a spin. And spin is just a shorthand name, basically, for a magnetic field. So usually or sometimes I should say, you'll see spin drawn like this, right? So spin up generates a magnetic field pointing in the up direction, and it corresponds to sort of like clockwise rotation. Spin down is counterclockwise. That is not an accurate picture, right? Spin does not correspond to literal spinning of the electron. It hasn't been measured. It would be extremely hard to measure that kind of thing. But this is generally speaking not an accurate picture. When you hear the word spin, you should just forget the English definition of that and just immediately think magnetic field. Spin is just a small magnetic field that is inherent in an electron. So the way that I like to think about it is each electron is kind of like a small bar magnet, right? So here I would draw, north side up there, south side down there. And if it's spin down, then the north side is on the bottom and the south side is up top. Okay. So now that we've got a little bit of that out of the way, let's talk about the actual Stern-Gerlach experiment. Suppose we want to measure the spin of an electron. How might you do that? Well, it turns out that we can utilize another magnet to sort of infer what the spin of the electron must have been. So here's the schematic that we showed in the lecture. The basic setup is that you have some kind of magnetic field. So here, magnetic fields, by the way, always flow from north to south. So if you're ever confused about like which direction the arrows go, it always goes from north to south. So in this picture, the arrows are pointing up. The other small technical detail I will mention here, just so it doesn't confuse people later, this magnetic field is not homogeneous. In other words, the strength of the field up here is not the same as the strength of the field down here. The field actually gets stronger when you get toward the south side of the magnet. So you can imagine this as, very little magnetic field on the bottom, and it gradually gets bigger until there's a very large magnetic field up top near the south side of the magnet. Okay, now we send an electron through this. The interesting thing about quantum mechanics is it tells us that the electron's spin will always be in one of two directions. It will either be exactly aligned with the magnetic field, or it will be opposite to it. In other words, the electron spin will either be up in the same direction as the magnetic field, or it will be exactly down. What it will not be is measured to be like sideways or something. It will always be aligned with the magnetic field of the Stern-Gerlach machine. Okay, so what happens? Well, yeah, so when you pass it through this, sorry, actually, let me clarify what I just said. The electron spin before it goes through this machine could be in any direction, right? So we could have a spin that looks like this. But by the time it passes through the magnet and it goes through this magnetic field, when it comes out the other end, it will either be spin up or spin down. When it comes out the other end, you will never see it still in some other direction of spin. Okay, so let's just quickly review some notation on this Stern-Gerlach experiment. We will often talk about measuring along one axis or another. So what we just saw is measuring along the z-axis. And the reason for that is that the direction of this magnetic field, this north-south magnet thing, those magnetic field arrows are pointing in the vertical Z direction. Now, when we are pointing in the vertical Z direction, there are only two measurement outcomes, like I said, and those two measurement outcomes are represented by these quantum states. So for example, we have the spin up state, which just means that when the electron comes out the other side, its spin is facing up. We usually assign that to be ket 0, which we're already familiar with. It has that vector notation. Now, what's the other possibility? The spin could be facing down. And in that case, we assign it to ket 1 with this vector. Now, you'll sometimes hear different words used for this. We could say that we're measuring along the Z axis. You might also hear someone say you're measuring in the Z basis, right? Because this 0, 1, as we learned before, is a basis. But all that really means, and this is one way that I like to think about it, a basis is essentially the possible outcomes. Again, because the spin will always be either spin up or spin down once you pass it through the Stern-Gerlach machine, those are the only two states that you will ever measure, spin up or spin down. Okay, what about other axes? We could, for example, measure along the x-axis. Remember what I said before, when we say that we're measuring along a particular axis, we're talking about the direction of these magnetic field lines. So if I measure in the x direction, what would you expect? Probably you would expect that the magnetic field lines, instead of going up and down, will now go left to right. And so we would literally just rotate this picture. It's kind of corny, but there you go. Rotate the picture, and now you have magnetic field lines going from left to right. And we would call that measuring in the x direction. Now, once the electron goes through this Stern-Gerlach machine, it's either going to be spin right or spin left. Again, aligned or exactly anti-aligned with the magnetic field. We usually make these assignments. So spin right is ket plus, which we've also seen before, and it has this vector notation. And then if it's spin left, we call that ket minus, and it has this vector notation. Okay, so I might actually just pause real quick and see if there's any questions. I see that you all have been answering each other's questions. Thank you so much for doing that. Okay. Does measuring not, oh, okay, this is a really good question. Does measuring not change the spin in any way? So I almost misspoke on this on the previous slide. So I'll correct myself one more time just to make sure that this is clear. The electron spin before it goes into the Stern-Gerlach magnets could be in any direction, right? So for example, maybe my electron spin is like a bottom left spin before it goes into the magnets. Now, once it goes through the magnets, that is called our measurement, right? So we'll see why this is called a measurement in just a second. But going through these magnets is a measurement. And by the time it comes out, it's either going to be spin up or spin down. So in this case, the measurement does affect the spin, right? So for example, suppose it comes out as a spin up on the other side. We have changed the spin from being, down left to now being spin up. Okay, if the magnetic field is not uniform, will it change the results? So the magnetic field here is actually already not uniform, right? So the magnetic field near the top here is stronger than at the bottom. And we'll see why that is important in just a moment. Is this somewhat analogous? Yes, thank you, good point. So somebody direct messaged me, they say, is this somewhat analogous to passing photons through polarizers, how they get aligned in only one direction? Exactly. If you are familiar with photons and polarizers and stuff, you can picture these experiments in the exact same way. It behaves the same mathematically, and you'll always get the same answer. If you don't know about photons and polarizers, that's fine. We're teaching you this version, the Stern-Gerlach version. But the photon polarizer version is an equivalent and perfectly valid way to look at things. Absolutely. Okay, cool. I am going to move on then, because the last section we have is some examples of the Stern-Gerlach machine. And by the way, you're going to see a lot of this type of question on your homework. So I'm going to try and spend some time going through these example problems. Okay, so let's look at the first example here. We have an experimental setup where we have an electron spin pointing up. So notice here, we're told that it's spin up. So I'm just going to denote that for myself with an up arrow. And we're passing it through a Stern-Gerlach, SG is just short for Stern-Gerlach machine, along the z-axis. And so here you can see, these two things are equal. Sometimes we will abbreviate it by just saying Stern-Gerlach Z. But what that really is it's a magnet aligned in this direction. So the magnetic field lines go up. Okay, so as I said before, the way that I like to think about an electron is as a little bar magnet. So it's got a north and a south like this. And the reason I know how to draw it like this is because, again, magnetic field lines go from north to south. So they look like that. And indeed, that is a spin up electron. Now, when this electron goes through the Stern-Gerlach machine, what is going to happen? Okay, so the only rule we need to know here is that north, like opposites attract, right? With magnets, north is attracted to south, north is repelled from north. So when the electron goes through the Stern-Gerlach machine, again, it's like a little bar magnet. The north and south are going to attract. And the south and north at the bottom are also going to attract. Sorry, I know this drawing is really small. Anyway. So because both of these are opposites, both sides are going to attract. But here is where this inhomogeneous magnetic field comes into play. Because the magnetic field is stronger at the south side, the attraction on the top will be stronger than the attraction on the bottom. And so what will happen is our electron will come in the middle and it will be attracted toward the south magnet. So it flies up and hits position 1. Okay, so I'll repeat that one more time. Our magnet is aligned so that north is on the top, south is on the bottom. Opposites attract, so the top is going to have an attractive force. The bottom is also going to have an attractive force. But because the magnetic field is stronger toward the top, the attractive force on the top is going to be stronger, and it's going to direct the electron toward the top of our screen. That's why the inhomogeneous magnetic field is used, exactly. Because if this field was uniform, the attractive force on the top and the bottom would be the same, and then it would just hit the 5, and that's not really that interesting. So you need an inhomogeneous magnetic field to show whether it was spin up or spin down. How are we assuming that all electrons are vertical? Could it not be, let's say, 30 degrees? Yes, it could be. And we will get to that in just a moment. This is just like a warm-up problem. Okay, cool. So let's go on to a second problem. And this time, I'm going to ask all of you to give an answer. So here is the exact same question. The only difference now is that the electron starts off spin down. Okay, so I'm going to launch another poll. Here, the electron is spin down. I'll start to do the setup, and then I'll give you a few seconds to work on this problem yourself. So again, the way that I like to start drawing is I will draw the magnetic field line going down. And again, the magnetic field always goes from north to south. And so in this case, the bar magnet would be drawn like this. South up here, north down here, because then when I draw the magnetic field line going from north into south, it is pointing in the down direction. Now, what happens when it goes through the Stern-Gerlach magnets? Which position does it hit? I will wait until about 50% of you have answered the question, and then I will show the solution. Okay, cool. So it looks like this is a faster question, obviously. There's no math to do here. Now, I'm going to use the same logic that I showed before, right? So when the magnet goes into the Stern-Gerlach machine, now it's the other way around. So we have south on top, north on the bottom. This time, there is going to be a repulsive force, right? South repels south, north repels north. And so on the top and the bottom, there will be a repulsion. But again, because the magnetic field is stronger on the south, the repulsion from the top will be stronger than the repulsion on the bottom. And so the electron is going to be pushed away from the top and travel down toward position 3. That is the correct answer here. Okay, let's go on to another example. This is another Zoom poll. So again, I'm going to ask you all to do this. I will just give you a heads up, though, that this is a pretty tricky question, unless obviously you already know the answer, which is fine. If you're just trying to think through this yourself, it's quite a hard question. So again, I'm going to do a bit of setup, and then you can go ahead and vote on the poll. Now here we have an electron that is in a superposition of 0 and 1, right? So in some sense, it is both spin up and spin down at the same time, right? It's got the north-south magnet and the south-north magnet in it at the same time. And here, this 0.71, by the way, is just 1 over root 2. So it's a 50-50 superposition of ket 0, so spin up, and ket 1, which is spin down. Okay, so again, I'll wait until roughly half of you have answered, and then I will explain the answer. Okay, let me look at some of the questions. So are electrons behaving as magnetic dipoles, and and the magnetic field applies a torque to it? Exactly, yes. So again, no worries if you don't know the physics behind that exactly. All you really need to know is that, opposites attract, and you can reason through these problems. But yes, that is correct. Is there any chance for electrons to get stuck between the magnets due to a magnetic force between the electrons and the bar magnet? Not really. And the reason for that, I think, is just that the electrons are usually moving so fast, right? So I'm kind of exaggerating the drawing here, but really these electrons would be fired at some insanely high speed, and the deflection up or down would be fairly slight, right? Like it wouldn't be this massive curving. It's just a fairly small deflection because the electrons are only in the magnet for a small period of time. Yeah, so I don't think they would ever get stuck in any sense. Okay, so let's see. Yes, 50% of people have answered. So let me go ahead and give an answer to this question. Now, the way I set it up here is in my opinion, sort of the correct way to think about it. And that is, as I said, to think about it 50% spin up, 50% spin down. And so the answer is that 50% of the time, it's going to hit position 1, like we saw in the first slide. And 50% of the time, it's going to hit position 3, like we saw in the second slide. So why did I say this is a tricky question? Well, a lot of people, if they don't have that set up, you all actually did pretty well on this, but a lot of people will say that it should be position 5. Now, why would you say that? Well, some people would sort of imagine the spin up and spin down almost canceling out, and then the magnets having no effect. That is not what's happening here, right? And this is a difference between classical and quantum mechanics. Classical physics would indeed predict that you hit position 5. Quantum mechanics predicts that you hit positions 1 and 3. The reason is that a superposition is not just sort of, an average of those two states. A superposition is literally you are in both of these states at the same time, and there will be a probability of sort of behaving like one or the other. So to all of you who said 1 and 3, that is very good, correct. Position 5 is correct classically, but not in quantum mechanics. In quantum mechanics, we have superpositions, which makes 1 and 3 the correct answer here. Okay, hopefully that made sense. We have one more question here, although this one in theory should be easier. Now we have an electron which starts spin up, so that's fine. And it's going to go through a Stern-Gerlach in the x direction, right? So here, my magnetic field lines are going from left to right. Where are they going to hit now? Well, the one thing that I'll say that will hopefully make this make sense is that this is the previous diagram flipped by 90 degrees, right? So literally, we are just taking these magnets here, flipping them 90 degrees. Now, our electron, though, is in the spin up state. How is it going to react to a magnet in the x direction? One thing that I did not explain here is that mathematically speaking, you might have even noticed this yourself. What is this state? This state is 1 over root 2 ket 0 plus 1 over root 2 ket 1. And you recognize that, or you might recognize that. That is just ket plus. And so another reasonable way of drawing this picture would be to show that your spin, so by the way, ket plus was spin right, remember? Another reasonable way to draw this picture would be to show the electron in the spin right configuration. Now, in my opinion, this can get confusing because here, if you draw it, spin right, it can be tempting to say that the magnet is going to have no effect, right? Because the north and south poles are not sort of near each other and causing this repulsive effect. But again, the way to think about it is that spin right is a superposition of 0 and 1. And so you get a superposition of the 0 and 1 outcomes. Going back to this question then, the way to think about it is that spin up in the x basis is a superposition of ket plus and ket minus. Oops. So you can work this out for yourself. You can actually plug in these definitions, but this thing is actually equal to ket 0, which is equal to spin up. And so when we pass a spin up electron through an x Stern-Gerlach, we get 50% going to the right and 50% going to the left and 50% going to the right. So to all of you who said 2 and 4, you are indeed correct. All right, so just as a general hint, I guess, on these problems, the correct answer is never going to be 5. Let's just get that out of the way. Electrons always have this spin. Remember, we said spin was a fundamental property of an electron. There is no way of sort of deleting the spin and making it have no effect, right? The spin is always going to be pointing in some direction, and you can always break that direction down as a superposition of the direction of your Stern-Gerlach machine. So one person asked, what about 1 in this case, ket 1? Would it be the same? So I would encourage you to think about that. If we start off in the ket 1 position, you can do the math here, and you'll find that the only difference is that this plus sign turns into a minus sign. This, however, is still a 50-50 superposition of spin right or spin left. And so you would still get the same answer, 50-50, 2 and 4. Okay, so yes, to all of these questions about what if we use 2 detectors, one in the Z basis and the other in the X basis, great questions. So I'm going to do my best to try and answer this because you are going to see some questions on the homework that have multiple Stern-Gerlach machines sort of lined up in a row. Now, the way to think about it is these diagrams we've been drawing on the right here, where we say it goes to 2 or 4 or 1 or 3, those are basically saying what the spin of the electron is when it comes out of the Stern-Gerlach machine. So if it came out here and it hit the 2, then it's a spin left. And if it came out here and hit the 4, then it's a spin right. And these happen with 50-50 probability. So if maybe I take all of the electrons that would have hit 4, and maybe I feed them through, I don't know, a Z Stern-Gerlach as an example. What would happen then? Well, then we have the same problem that we saw on the previous slide. It's just a spin right electron going through a Z Stern-Gerlach machine. So with all of these, you just kind of have to reason out what direction the spins are going to be. And you'll always end up with a problem that's something like, oh, if I have a spin right electron going through a Z Stern-Gerlach, what happens what happens on the screen on the side? And we've gone through all of those examples. The only example that we haven't gone through here is if you, or actually, no, I guess we did go through that. Yeah, no, we've gone through all of the examples. So you should be able to do everything with the questions that we've given you here. But when you have multiple Stern-Gerlachs strung together like this, I would highly encourage you to think of them just one at a time and sort of track through what will happen, right? So the first one, spin down, goes through a Stern-Gerlach X. The result is going to be either spin left or spin right with probability half. Okay, that's step one. Then you would go to the second Stern-Gerlach machine and say, what happens if I had a spin right that went through it? What happens if I had a spin left that went through it, right? And so you can do these kinds of thought experiments to figure out what a whole chain of Stern-Gerlach machines would do. Okay, can we measure in the y-axis? Usually not, just because the y-axis would be, it's not aligned to the direction of the electron's movement, right? You can only measure z or x. So I think the answer is no. At least for our purposes, the answer is no. Is the spin perpendicular to the magnetic field? No. So the spin is always going to be parallel to the magnetic field. For example, in this experiment here, the outcomes on this side of the screen are either spin right or spin left, right? And right and left are the two parallel directions to the magnetic field. Is the magnet shape necessary? Oh yeah, so these diagrams, they draw the magnets with kind of like a point on the S and a valley on the north. That is just, that's one way of showing that the intensity of the field is higher on the south side. I won't get into why that is, but yeah, I mean, I would just kind of forget about that fact. It's just a schematic way of saying that the intensity of the field is higher on the top. How did we know the magnetic nature of spin, as you wrote in the initial properties of the electron, since this experiment was the one which validated it or discovered it? Yeah, that's a good question. I think the best answer is through this experiment, we realized electrons must have some magnetic properties, right? We can look at the outcomes of these experiments and we can reason that an electron must be kind of like a bar magnet to get these deflection properties. Now, further questions on what exactly spin is and how it changes, and the fact that it is a quantized thing, right? So you can have a superposition of it. All of that, I think, requires more experimentation for sure. But Amir said in lecture that the magnet is formed in this shape to make sure the magnetic field goes in a straight line from north to south. That could be another fair description. I think I wouldn't worry too much about the shape of the magnets or the way that they're drawn. The key property is that the magnetic field lines go from north to south, and that the magnetic field is stronger at the north side than it is at the south side. However you want to remember that or draw that is up to you. Okay, so yeah, one person says, I can't fathom why ket, what was the question, sorry, ket1? Sorry, ket minus is 0 minus 1 over root 2. So for all of these superposition states that I mentioned here, so for example, this equality, you can just go ahead and check this, right? Plug in the definition of ket plus, for example, or back here, where was it? Yeah, here you can plug in the definitions of ket plus and ket minus, and you'll see that all the ket ones cancel out, and you're left with only a ket 0. Okay, so I am going to get back to questions in just a moment, but let me just finish the lab so that people can go if they need to. Just some key takeaways. This is the last slide, by the way. In the first half of the lab, we talked about how measurement in the quantum world is different from everyday life. As I said, the key takeaway here is just that measurement in the quantum world can affect quantum states. In the second half of the lab, we looked at the Stern-Gerlach experiment. And this is basically a way to measure the spin of an electron, right? So when measured, and I guess I should clarify just to be very explicit, the reason we say that this is measuring the spin is that we know based on where the electron appears, what the initial spin of the electron is, at least to some extent, right? So perhaps the easiest way to see that is in the first two experiments. Oops. So here, because the electron hits position 1, we knew it was spin up in the beginning. Here, when it hits the down position, we know that it's spin down. If it hits, the spin up, position 1 and position 3 sometimes, and there's some probability distribution, then we can infer that it was not perfectly spin up or spin down, but some superposition of the two. Okay, yeah, I think that's all of the key takeaways. All right. So further readings and resources. Again, this is just sort of some further reading that you can do if you like. All of these are related to what we talked about. This one in particular is a really cool lecture if you do want to take a look at that. I'm sure all the other ones are cool too. And that's the end. Okay, so I'm going to throw up the post-lab Zoom poll, and then we'll keep answering some questions. Because I think I want to spend a lot of time on Stern-Gerlach because it is it can be confusing to wrap your head around for sure. Okay, so I'm going to go back to the questions. Okay. What if we put the magnetic field horizontal and the spin vertical? So we did go through an example like that. It was, actually, what did you ask? Magnetic field horizontal and spin is vertical. So that's what we did right at the end here, right? So in this case, the electron spin was up, the vertical spin, but the magnetic field is horizontal. And what we see here is, again, there is a 50-50 chance of hitting 2 or 4 because spin up is a superposition of spin right and spin left. Hopefully that helps. Okay, these bases are not physical and relate to the basis with respect to the Bloch sphere, right? Yeah, so these bases do relate to the Bloch sphere, absolutely. I think that you can think of them physically as well. I think it kind of works in both ways in this particular case, because when you have an electron that is spin right, for example, you really can think, well, yeah, okay. No, I think you're right. It probably works best in the Bloch sphere picture, probably not as a physical interpretation. Okay, how is it possible to generate an electron that is specifically spin up or spin down? Good question. Usually the way that works is we generate a whole bunch of electrons in multiple spin configurations, and then we apply some strong magnetic field that will align them either with or against the magnetic field. So actually I can pretty much just show you how this would work because it was the first example. So if we wanted to generate spin up electrons, well, actually, it would look something like this. Your electron state at the beginning could be anything you want, right? You can just randomly generate electrons and they have spins going every which way. But when it comes out of the Stern-Gerlach machine, remember, there's only 2 possibilities. It will either be spin up or spin down. And so what you could do is you could just put like a little collector on top here, and you'll know that every electron entering that collector has to be spin up. So that's how you might do it. North or south is stronger. The south side is stronger in this magnet. Good point. Oh yeah, somebody answered, sorry. All right, what if we put the magnetic field horizontal and the spin vertical? I answered that. What makes 2 qubits entangled? That is a much longer answer that I will not go into right now, but feel free to ask on Piazza for sure. Okay, let me just take a sec to read this question. You add two magnets and use them for two different measurements depending on the direction. Correct. Yeah, this is a good point. So the thing that matters with the Stern-Gerlach experiment is the orientation of these magnets, right? So we're not changing anything else. We're literally just rotating these magnets to be aligned vertically or horizontally. And that's what causes the differences in our measurements on the screen. Yes, the recording for this lab will be available. I don't understand how we're writing these ket forms. Okay, so I would recommend, well, I can just write you a very quick summary. The only equalities that you'll ever need to know for Stern-Gerlach are these. So ket 0 is 1 over root 2 ket plus. It's 1 over root 2 ket minus. And eventually you'll just come to memorize these because they are, you'll see there's a pattern. And ket plus. So those four equations are the only things that you'll ever need for Stern-Gerlach, basically. And so if you look back on the previous slides, I'm always using one of these equalities. You can go ahead and check for yourself that all of these hold and match the definitions that we've been working with. But it also suffices to just use these equalities whenever you need them. Okay, so regarding the earlier question, why ket minus is ket 0 minus ket 1? Can we visualize it using Stern-Gerlach? So I think the easiest way to see why ket minus is ket 0 plus, or sorry, minus ket 1 is just to work it out mathematically, right? Like actually write down the column vector forms of this equation and you'll see that it works. As far as visualizing it though, you can visualize it on the block sphere. Absolutely. And so if I just draw a quick block sphere here, so it'd be something like this, Z, X, oof, it's hard to draw. Anyway, okay, so you'd have a block sphere, something like this. And we are looking at the ket minus state. Okay, so ket minus is just anti-aligned in the X direction. So it's gonna be over here. Now you can kind of think of this as an average of ket 0 and ket 1 in some sense, right? Like it's sort of halfway between ket 0 and ket 1. Now you'll also notice that ket plus, which sits down here, if I had drawn my drawing better, but ket plus is also halfway between 0 and 1. So that's why, when you do the Stern-Gerlach experiment with an X-aligned magnet, spin up or spin down both produce the same result. They're both going to produce 50-50, 2-4. Yeah, I don't know if this is necessarily the best way to visualize it, but that's the best thing I can think of right now. Okay, so maybe I'll answer one more question here, just so I don't go too long. If ket 0 is the superposition of spin left and spin right, can we simplify the spins to only be spin left and spin right? Yes. And so you can always write an expression that has ket 0 and ket 1 in terms of ket plus and ket minus using these first two equations, right? You literally just substitute everywhere a ket 0 shows up, plug in the first one, everywhere a ket 1 shows up, plug in the second one, and then your whole equation will be in terms of spin left and spin right. So because Z and X are both bases, remember, you can always write any quantum state as a superposition of basis states. Because these are bases, you can always write a quantum state as a superposition of spin up, spin down, or as a superposition of spin right, spin left. All right. Jessica Yuan's question. I checked Google and it says the magnetic field is equally strong at both poles. Is that different from what you mentioned? It sounds different than what I mentioned. The Stern-Gerlach experiment should have a stronger magnetic field on the south side. That's why we see the deflections that we see. Yeah, I'm not sure about exactly the resource you're looking at. Perhaps though, if you post it on Piazza, we can take a closer look. Okay, so one person says, when does the electron land at position 5? And somebody else correctly says, I don't think it does. So that's kind of the hack with these types of questions. It's never going to be position 5. You can always have that as a rule. If you ever think, oh, it makes sense in this case that it should be position 5, you should probably be thinking of a superposition instead, right? So it'll be a superposition of 1 and 3, for example, instead of position 5. Okay, cool. I think that's most of the questions. Thank you for the compliment. This is, yeah, Stern-Gerlach questions are notoriously confusing and kind of hard to do. So I would strongly encourage you to just rewatch these 4 slides, like the 4 examples that I gave here. That, I promise, will cover every single case that you'll see on the homework. You might just have to, do a rotation in your head or think a little bit about it, but these 4 cases cover everything. Okay, cool. So I'm going to stop doing questions there, but I'll go on to the bonus content. If you do want to rewatch any parts of this lab, though, the whole thing will be uploaded to YouTube, and I'll send out the little announcement with a YouTube link later on today. So you can rewatch any parts that you were confused by. All right. So let's go on to the optional content, which, like I said, thankfully is pretty short this week. So we just wanted to spend, honestly, a few minutes talking about 2-level systems. Now, I'm going to start off with asking, why do we care about 2-level systems in quantum computing? The clear answer to this is that qubits are 2-level systems, right? So just like in the classical world, quantum bits can be either 0 or 1. And because they have these 2 possible states, we call it a 2-level system. I guess physicists aren't exactly the most creative with their naming, but because it has 2 basis states, it's called a 2-level system. Now, one question that comes up a lot is, well, why don't we use a 3 or 4 or 5-level system? Wouldn't that be even better and more powerful? There's a couple of answers to this. The first answer that I hear a lot is that we use 2 levels because that's the way classical computers work, right? In classical computers, everything is a 0 or 1, and we just wanted quantum computers to be kind of the same as classical computers. As far as I know, that is not actually all that accurate. There are better reasons for why we use 2-level systems. Probably the biggest one is that it's really hard to control a 3 or 4 or 5-level quantum system. The reason for that is that you often have to have 2, so for example, like 2 magnetic fields, right? You would have one magnetic field value that is tuned to be ket 0, and one magnetic field value that's tuned to be ket 1. In order to make your experiment easier to run, you want those 2 values to be as far apart as possible, because you want to be able to measure the difference very easily. If you add a 3rd level to that system, the difference between each of your levels gets smaller and smaller and much more difficult to actually measure correctly. So this is what we mean by, it's harder to control something that has more than 2 levels. It's just because the instruments you would need to sort of operate at such a fine fidelity are just a lot more expensive and complicated. So for the time being, yes, we're using 2-level systems. There are some, relatively uncommon types of quantum computers that use 3 or more level systems. They do exist. But as far as we know right now, 2-level systems achieve the best balance between cost, complexity, and power. And that's really the reason why we use a 2-level system. So I think this should probably be nothing new to anybody here, but just to explain what I mean by a 2-level system, it has 2 different states, right? So like the world's shortest staircase, you can be on this stair or you can be on that stair. A light switch can be either on or it can be off. Transistor can be charged or discharged. These, however, are all classical two-level systems. For some examples of quantum two-level systems, these are basically things that we use for qubits, right? So one that we already talked about is electron spin. There are systems that use electron spin as the qubit, right? Ket 0 spin up would be 0, Ket 1 spin down would be 1. And we already saw in the Stern-Gerlach experiment, we can have superpositions of spins. Therefore, this counts as a quantum two-level system. The double slit experiment is actually another two-level system, right? You can think of it as being, going through the left slit or the right slit as being the two levels. And although I don't think anybody actually does this in practice, you could, in theory, build a quantum computer around that, where a 0 is if it goes through the left and a 1 is if it goes through the right. If you've heard of superconducting qubits, that is another example of a two-level system. The difference here, though, is that the two levels are the direction of current flow in a loop. So if the current is flowing counterclockwise, or how does it go? I actually don't know. But yeah, if it's spinning clockwise, I guess, then you call it down or 1. And if it's spinning anti-clockwise, then you call it up or 0. And that's just kind of a convention that is established for superconducting qubits. So the key takeaway, I guess, for quantum versus classical two-level systems is really just superposition, right? What makes something a quantum two-level system and therefore usable as a qubit is its ability to be in a superposition. So as we saw, spins can be a combination of both. A light switch, I mean, you could argue that you could balance it right in the middle, but for our purposes, a light switch is either on or off. Therefore, it's only a classical two-level system. So you can kind of think of this, I don't know if this analogy will help, but you can kind of think of this as two musicians playing two different instruments in the quantum world, right? One of them could be playing at a time, but you can also have harmonies created when both of them are playing their instruments concurrently. In the classical world, it's more like you have only one musician who can pick up one of two instruments and only play one at a time. They can't really play both of them at the time. That is really the difference between a quantum and a classical two-level system. And that's all I have to say on this topic. So I'll just quickly glance over at the questions. I don't think any of this is new per se, but I think it's just a good review because, of course, two-level systems are super important for quantum computing. Okay, so one person asks, I was thinking that regarding superposition in quantum states, it's not actually in both states, but it's constantly changing from 1 to 0 and vice versa. But since we could not measure it, we assume it's both. Is this a possible theory? I don't think it is, at least as far as I know. And so I imagine there's probably an experiment someone has done that somehow disproves that. I don't know off the top of my head what that would be, though, because I think, as you're saying, it could make sense that these things are just sort of rapidly oscillating, and they're oscillating so fast that we can't detect it, and we just say, oh, it must be in both at the same time. I would imagine that experiments testing interference of two-level systems would be able to disprove that, because if it only ever is in one at a time, I think that you would get different interference patterns. But I'm not exactly sure on that. So that would be an interesting thing to look up. Quantum computing with a 3-level system, does it have 0, 1? Oh, does it just have 0 and 1? So if you had a 3-level quantum computer, you would have Ket 0, Ket 1, and Ket 2. You just keep adding Kets for however many different levels you have. We haven't really talked about how the math of that works. That's a separate subject. But that's the basic idea. How about 8-level, step down to 4-level, step down to 2-level, and classical bits? Not sure I exactly understand the question. One thing I will say, though, is that oftentimes we will use a quantum system that has more than 2 levels, but we only use 2 of those levels for quantum computing. And again, the reason is just that it's a balance of cost and power, right? So it's a cost and ease of use as well. It's easier to just work with those 2 levels than to try and work with every level in the system. Are NMR spectrometers a 2-level quantum system? Yes. Yes, they are. I guess with NMR spectrometers, there are, oh no, I think that is just a straight up two-level system. As far as I remember. Anyway, I think that's actually a very good example of a 2-level system. Okay, is there any standard to set the basis in a way it is? One can have the basis in which someone can have electron in one state and someone can have the same electron in 0 state if we have the flipped basis. Yeah, good question. It's just a convention to say that 0 is going to be spin up and 1 is going to be spin down. You could totally have it the other way around. It wouldn't change anything. It would just confuse people. So we have a standard. That's the only reason. So I was a quantum enthusiast when balancing switches in childhood. Yes, exactly. You were discovering superposition. All right. Oh yeah, this is a good point. Bell's inequality. Would that prove anything for the sort of like flipping spins up and down? It very well could. That is a good point. So I was thinking maybe interference. I bet entanglement would be another one where an entanglement related experiment would give you some kind of proof against that fast oscillation theory. Are the levels dimensions? So usually the answer to this is actually yes. So if you had a 3-level system, if I can just digress a little bit here, but the way that you would represent these as vectors would be with 3-dimensional vectors. So it would look something like this. Right, and then those would be your 3 basis states, those are your 3 levels, all that kind of thing. Is it possible to have more than 2-level system in quantum computers? Yes, it is. It's just a relatively rare approach right now. Multi-level systems are simulations, or no, they actually exist. And I think probably the best example of this, or maybe one that will be familiar to some of you, is with electron orbitals. So one type of quantum computer is called a Rydberg quantum computer. And basically what that means is you have atoms that are fairly large, right? So their atomic number will be like 80 plus. And the way that you have your 2 levels is you either have an electron sitting in the valence, right? So you'll pick something that has 1 valence electron, for example, right? And there'll be a bunch of other levels inside that. And this 1 valence electron can either be sitting right here on the outermost orbital, or you can do a procedure to excite it to a much higher orbital, say something like way out here. And those would be your 2 levels. You either have electrons sitting relatively close to the nucleus or relatively far away. And you can manipulate those. Turns out it can be in a superposition, all that good stuff. However, you could, in theory, if you had really precise instrumentation, you could use every electron shell, or sorry, not direction. You could use every electron shell outside of this outer shell to be a level, right? You could excite this 1 level up, you could excite it 2 levels up, you could excite it 3 levels, 4 levels, 5 levels. You could have, potentially dozens of levels in this system. But the precision you would need to sort of differentiate between these levels of an electron is just far beyond what we have right now for any reasonable amount of money. And so the easiest way to do it is just pump the system full of tons of energy and send the electron up to some crazy high level, and then do the same thing in the reverse direction to get it back down. It's a very coarse approach, but it gives us a 2-level system. All right. Yeah, so I just talked about more than 2-level system. And actually, the Rydberg system, I should say, is technically a 3-level system. Well, people call it sort of a 2.5-level system. I won't get into why, but it is the case that when you're doing these sort of transitions, sometimes they will use an intermediary state to do certain things. Again, I won't get into it, but there are real-world examples where you have multiple levels, but usually it's distilled down and it's simplified so that there's only 2 levels. Okay. Every level isn't a physical dimension, it's an abstract dimension of probability. Yeah, oh, I see what you're saying. Yeah, that's a good point. So these different levels that I'm talking about, the dimensions that I was referencing are abstract dimensions, right? They only become dimensions in a sense when you go to linear algebra. If you had, you can totally have a 5-level system, and algebraically speaking, those would be represented with 5-dimensional vectors. It doesn't mean that those, that object somehow exists in 5-dimensional space. It's still just a 3-dimensional world, obviously, but we use 5-dimensional vectors to represent the superpositions appropriately. Why don't we use hydrogen separately as the first level and ionized helium as the second, and so on? I'm not familiar with the precise answer to this, but I would guess that it is a question of how precise you can make those transitions. Now, in the case of hydrogen and helium, I would actually guess that it's pretty easy to make those transitions, just because I know that's a process that's done a lot in industrial fields. Another guess for why that might not be a viable quantum computing strategy is that on top of addressing things between these 2 levels that can be in superpositions, you also have to be able to entangle them somehow. Now, methods of entangling qubits differ wildly between different platforms. It can be something as simple as Coulomb repulsion that explains why things get entangled, all the way up to extremely complicated theories about nonlinear inductance in superconducting qubits. With some of these things that might look like a good 2-level system, if they're not used in practice today, I would guess it might have something to do with either not being able to control the 2 levels very accurately, or not having a good way to entangle them. Those are kind of 2 major sticking points for a lot of quantum implementations. Okay, cool. So I think that's all of the questions. I will wrap things up there. It's always fun to talk with you all, so thank you for the good questions. If you have any more, of course, feel free to post them on Piazza. But as well, if you just have basic questions about the homework, we definitely want to help you with that too. I know the Stern-Gerlach questions can be quite confusing. So with that, I will end off the lab, but good luck on the homework this week. Again, please post on Piazza if you need help, and we'll see you again next week. Have a good one.